let's start.
Okay, thank you, Tobias. Hi, my name is Moha, and I am a scientist at NCAR in Boulder, Colorado. Thanks for the opportunity to speak to you today about our data simulation software, Dart. Okay, so first I'll introduce Dart, talk about some of the algorithms, and show you some cool recent applications. My colleague Helen will then take over and tell you more about the software and that Dart uses. Okay, so to begin with, Dart is an open source, flexible, and freely available community facility for ensemble data assimilation. It is developed and maintained by the Data Assimilation Research section, which I am part of at NCAR, and has been up and running since its first Easter release in 2004. Everything you need to know about Dart can be found on our webpage. All of the Dart new and improved documentation can be accessed here on docs.dart.ucar.edu. You can also get an overview of Dart using this featured 2009 BAMS article. Okay, so getting to know Dart. Dart as a data assimilation tool is well tested and has been applied in a wide variety of applications. The source code is distributed on GitHub with a large user base consisting of 50 universities and more than 1,500 registered users. We also offer extensive data assimilation teaching and tutorial material. In terms of the framework, we work with many different models and observations. We do not touch or change your model, and often new models can be added in a matter of 2 to 3 weeks. Dart is an easy-to-use product, and you really don't have to be a data assimilation expert to play with it. It can be run efficiently on laptops and supercomputers, and later in the talk, Helen will give you more insights on about its exceptional performance. We always welcome users' contributions through GitHub issues and pull requests. Here are some of the geophysical models that are interfaced to Dart. Hopefully you can find your favorite one. As you can see, they are distributed based on their functionality in the environment. For instance, WRF Hydro studies stream flows, while WACAM-X looks at the whole atmosphere, including the thermosphere and the ionosphere. Models in red are models that are recently supported in Dart, such as FESM and NOMP. Dart also includes many low-order toy models that are mainly used for theoretical development and educational purposes. Similarly, here are some of the Earth system observations that can be used in Dart. Actually, several of these, represent data sources rather than the platforms that actually took the measurements. Again, everything you see in red are observations that have been recently added in Dart, such as radiance observations and ocean color. Okay, so next up, I'd like to show you some of the many applications in Dart, and we start here by the atmosphere. So I'm showing 4 different applications. For instance, the WRF and AMPAS in the top right corner here are used to study convection permitting data assimilation at both regional and global scales. This work has been led by Craig Schwartz and Glenn Romine. Nick's work here focuses on coupling WACAM-X and Dart. It illustrates the importance of data assimilation in the upper atmosphere using cosmic data to improve electron count forecasts. Tammy is leading efforts to assimilate a new instrument MPD data or micropulse differential absorption in WRF. This is primarily used to improve estimates of water vapor and precipitation. Now, on top of forecasting, we also just finished conducting a 10-year atmospheric reanalysis using a 1-degree CAM. The effort was led by Kevin Rader from the DERS team. This reanalysis provides a large data set consisting of realistic atmospheric ensembles that can actually be used to force other Earth system components such as the land and the ocean. Okay, so coming into the ocean, I'm showing here 2 examples. On the left this is the Red Sea Initiative, which is a collaborative effort between NCAR, Scripps, and KAUST. The forecasting system couples WRF, MIT GCM for the physics of the ocean, MBLINK for the biogeochemistry of the Red Sea, and WaveWatch 3. So the goal is to hopefully build a fully coupled high-resolution data assimilation framework for the Red Sea region. On the right, there's a global ocean data assimilation effort that's led by Fred at NCAR, using a 1/10 of a degree pop ocean model and Dart's ENOI or ensemble optimal interpolation capability. You see in the top like typical observations that are simulated and some of the results here at the bottom. As far as the land and hydrology go, Brett Raska and the DERS team uses CLM5 or the community land model to perform biomass data assimilation using Dart. the plan is hopefully to extend this and move towards assimilating water such as SWE, soil moisture, in addition to SIF or solar-induced fluorescence. Recently, DART has been coupled to the National Water Model, or WRF Hydro, to perform flood prediction during hurricanes that cause extreme rainfall events. The example I'm showing here is the flooding due to Hurricane Florence in 2018 that hit the Carolinas. Developing new localization strategies that adhere to the stream network, which is a highly irregular grid, was a big part of this work. Okay, so now moving towards algorithms in DART, it's important to mention that DART assimilates the observations serially or one after the other. This choice is made for practical reasons. It helps simplifies the computations and avoid the need to work with matrices and matrix inversions. In terms of filtering algorithms, we support more than 10 different algorithms in DART or filters in DART. Some of these are listed here. Obviously, the original stochastic eNKF by Ger Evensen, the ensemble adjustment combo filter by Jeff Anderson. We also support nonlinear and non-Gaussian variants, such as the quadratic filter by Dan Hodis, the GIG eNKF by Craig Bishop, John Potter-Joy's localized particle filter, and Anderson's rank histogram filter. Some new techniques that have been recently added include Gaussian anamorphosis and variation bias correction for radiances. Coming soon in 2022, two important assimilation algorithms will be added to DART. The first is the quantile conserving ensemble filter, which is a nonlinear filter, especially suited for estimating bounded quantities such as ice concentration. The other algorithm here is the adaptive hybrid eNKF-OI scheme, which essentially adds a variational or climatological flavor, if you like, to the standard eNKF. Because we work with ensembles, we also provide additional enhancements to tackle a variety of issues, such as sampling errors. These include prior and posterior inflation with spatially and temporally varying adaptive forms, horizontal and vertical localization with different correlation functions, in addition to smart adaptive formulations, such as using empirical localization functions. Other useful techniques, such as sampling error correction and the use of hierarchical groups, are also provided as part of the DART software. Now, if you'd like to test some of these algorithms, we provide a number of GUIs that can be used for educational and learning purposes. These GUIs are part of what we call a DART lab, which is a tiny MATLAB version of the DART Fortran code. So this example I'm showing here from the Lawrence 96 model, the user can select, different assimilation algorithms, run simulation with or without model errors, specify localization, ensemble size, and test various configurations of the adaptive inflation scheme. The user can also change the observing network and assess the results by looking at the RMSE, spread, and the rank histogram. The GUI will go on just showing, what happens when you introduce model error. And for instance, if we turn off inflation, you will see that the system starts diverging. So the RMSE starts increasing and, we start losing spread. And then after we turn back inflation, and because the inflation is spatially varying and adaptive in time, it responds nicely and, tackles the deficiencies in the ensemble. And yeah, at the end of the GUI, there are tests of what happens when you use different observing networks in the system, and how the inflation reacts to that. And yeah, that's how it goes. Coming into diagnostics, 4 stages of assimilation are available in which state space assimilation results can be assessed. Within each stage, the individual member files, the ensemble mean and spread, and also the inflation files, if requested, are given. We also provide extensive observation space diagnostic tools and functions. These include time series and profile plots of RMSE, bias, spread, in addition to rank histograms. Tools that also display assimilated and rejected observations on geographic maps are also available. And now I'd like to give the virtual floor to Helen, who is our lead software engineer in the group. She'll talk to you about DART's infrastructure and implementation.
Hi, thanks, Moha. Hello, everyone. Moha's given many examples of the science accomplished with DART. So I'm going to talk about some of the software infrastructure and implementation behind this science. So first off, philosophically, DART separates the physical quantity from the observation type. So for example, U-wind component is a physical quantity, and the measurement of U-wind may be by radiosonde, maybe by satellite, or some future unknown instrument. The forward operator is then what the model predicts the observation should be. So for a given observation type, you've got a description of the observation, any associated metadata, and a definition of how to calculate that forward operator and the physical quantities you need to do that. What this does is it lets you use the same forward operator for, say, radiosondes, no matter which atmospheric model you're using. So MPAS, WRF, future novel model. And the forward operator might be relatively simple, just an interpolation for wind, or much more involved for something like satellite radiances. You can use existing Dart forward operators, there's about 50, or you can add your own and switch them out at compile time. The model interface is something you have to write when you add a new model to Dart. It's 17 subroutines. We do have default versions, you don't necessarily have to write all 17. And we modularize out location for you. So we have maybe 10 location models, 2D, 3D, Cartesian, spherical, annulus, periodic domains. So depending on your grid, you can probably use an existing location module. And so any optimization for distance calculations is already done for you by Dart. And for control, there's two options in Dart. Small models that you can just run as a subroutine in memory, like the RENS 96 can be run inside Dart. So this is great for research, great for teaching. And for larger models, you can run Dart as a separate executable inside whatever external workflow manager you're using. So for example, we have a lot of people run it inside CSM SEAM infrastructure, or you can, pick your favorite shell script, Python script, workflow manager, and run Dart. Next slide, please, Maha. So I'm going to talk about some of the data management we do in Dart, and the management of memory and the algorithms are intimately connected. So very briefly, here's the Dart algorithm. Forward operators are calculated up front. So before we do any assimilation, each observation is then sequentially assimilated. So the assimilation updates are applied to the state, to the model state, and to the forward operators for not yet assimilated observations. So this assimilation of the joint state plus forward operators is really powerful. So you don't have to do any matrix inversion or anything like that, which lets you work with extremely large models and scale very well. It does also mean that you can use externally calculated forward operators very easily with Dart. So we have people who use GSI forward operators, and you could use JEDI forward operators if you wanted to. But what we're concerned with here is memory management for forward operators that Dart calculates. And there's always this tension between how you'd prefer the model data to be organized in memory for a forward operator versus how you'd want it for assimilation. So assimilation, you want the whole ensemble and you only want a subset of the state. And ideally, for load balancing, you want to spread that model state out as far as possible. For a forward operator, you want the total opposite. So for something like GPS observations go through a large chunk of the atmosphere, you're going to need a large chunk of the model state to calculate the forward operator. So what we do in Dart is we solve this by keeping the data in the layout best for assimilation. This is where the bulk of the calculation is. Whole ensemble, subset of the state. And we use one-sided MPI communication to make that distributed memory invisible to the model interface. So the model asks for, say, temperature at X, Y, Z, and Dart just goes and retrieves that data for the model interface. This allows us to vectorize across the ensemble. So when you do a forward operator calculation in Dart, you're actually doing one calculation for 80 ensemble members, single calculation. And we've scaled that up to 70,000 cores. So we found that works really well for us. Next slide, please, Maha.
2 minutes left, Helen.
Yeah, perfect. So I just want to mention some initial work we've done at a NERSC hackathon in December. So a group of 3 of us went and worked on their new machine, Perlmutter. So we worked with some mentors from NVIDIA, got some really promising results. Because one sort of heavy computation in Dart is localization. So we only want to update the state within a certain radius to reduce any spurious correlation. So we took a little mini app there and got some really nice results. You want to do the next slide, Maha?
Thank you, Helen. So in summary, Dart is very flexible, research-focused, community ensemble data assimilation system. We work with many different Earth system models, and we focus on research, theory-based research, and we also collaborate with other scientists to do large-scale world applications. It's an excellent resource for learning data assimilation, and we would like to work with you. If you have an interesting project, interesting algorithm you would like to add, please get in touch with the Dart team, with us, and we will be more than happy to assist you. Thank you.
Thank you very much, Moha and Helen, for this informative talk. I learned something today, and yeah, I already see one question in the OPED. So if you have more questions, please have a look into the chat. There you find the link to the OPED where you can ask your questions. And so the question is by Lars Nerger, and he says, "Nice presentation, but does Dart actually handle correlated observation errors? Does no non-diagonal R matrices?" So could you comment on that?
So that's a very good question, Lars. Obviously, because we estimate the observations serially, you can't do that right away unless you go ahead and decorrelate the observations ahead of time, and then do some transformations to diagonalize R, and then assimilate the observations serially. So there's some pre-processing that should be done at the observation level ahead of running the filter in Dart.
Thank you very much. And then another question by myself. So do you try out scale-dependent or multi-scale localization schemes within Dart already?
Could you say that again?
So there's so many people apply scale-dependent localization, that they separate scale, let's say in the B matrix. So did you try something within Dart?
So there have been some effort by Michael Ying, who started doing multi-scale data assimilation. So he's developed some interesting algorithms that have been tested in Dart, but these are yet to be integrated.
Okay. And then the last question. So if I'm a new user and want to start using Dart, so how would you start? And is there are there training courses that you could attend as a new user?
So we provide a lot of tutorial material. If you go to the webpage, in fact, if you want to take a picture of this thing, it will take you there directly there. There are vast tutorial material in PDFs. We did some teaching courses at at workshops and conferences a couple of years ago. Since the pandemic hit, we haven't done that. But if you're interested, I would say start from the webpage, get in touch with the Dart team, and we'll take it from there.
Thank you very much. There's another question in the OPED, but we have to move on due to time constraints. So if you could go to the OPED and answer the question in written form, that would be very nice. And thank you again for this great talk and for staying awake so late. We really appreciate it.